I said last time, the scale-free network does not have any particular scale for the range of degrees. So, like, if you compare the two distributions, the Poisson distribution is this bell-shaped curve. And so you have a mean, the average degree, and most of the node degrees are around the mean. Okay, so we say the range is the average degree plus or minus the standard deviation, the square root of the average degree. Whereas for a scale-free network, the standard deviation is typically much larger than the mean. So for all theoretical purposes, we can say it's infinity. Okay, so you cannot say the range of node degrees average plus or minus infinity. It is a very large value. So as you can see, the distribution looks like this. So which means the average is typically a smaller value, but the range could be kind of endless. We cannot say there is a particular limit. Okay, so that's why they're called scale-free network. All right, let us do some math problems now. So consider a network model using power law. This is scale-free network. According to this relation, P of k equals C times e raised to negative gamma. So we need to determine this power law exponent gamma and the constant C. Okay, so those are two things we have to determine. And what is given? The network has approximately 4% of the nodes with degree 4 and 10% of the nodes with degree 3. So can anyone say what is given? What is this 4% of the nodes with degree 4? What does it mean? So you have some nodes, right? So among the nodes in the network, 4% of the nodes have degree 4. That is equivalent to telling the probability of finding a node with degree 4 is 0.04, the 4%. And 10% of the nodes have degree 3, so probability of finding a node with degree 3 is 10%. So this is what is given. The pk values for k equals 3 and 4 are given. Okay. So now we need to find the two values, the constant and the exponent. So how can we do this? So we can write P of k equals C times k to the negative gamma. So if you take logarithm on both sides, you know this, right? So if I take log on both sides, logarithm of P of k equals, so log of P of k equals log of C times k to the negative gamma. So when you have logarithm of say A times P is log of A plus log of P, right? So we can apply that property. So it's log C plus log of k raised to negative gamma. Now again, if you have something like this, so log of say a to the power b, we can bring the b outside like this and say it is b times log a. Okay? So we can do the same thing here. This is log c. So if I bring this negative gamma outside like this, minus gamma times log k. So this is log of P of k. Is that clear? So if we just apply the property of logarithm, log of c times k to the negative gamma is log c plus log of the second term, k raised to negative gamma. But anything like log a raised to b is b times log a. So this is minus gamma times log a. So now why we wrote it like this? Because we are given P of k for two different values of k. So this is known, k is known, P of k is known. So the only thing that we need to find is this log c. So it's like two equations, two unknown. So solving two simultaneous equations. Okay? So that's what I have done here. So if k equals 3, P of k is 0.1. So log of 0.1 equals equals log C minus gamma times log 3. Then log of 0.04 for k equals 4 log C minus gamma log 4. So you all know how to solve two equations like this, right? So this is natural logarithm, so the base e. So log of 0.10, the base e is negative 2.303 equals log C as it is minus gamma times log 3 is 1.098. Similarly, second equation. So how to solve them? You can just do like the first one minus second one, so log C can cancel out, okay? So we can get first the gamma, right? Well, now to solve this, isn't it? Yes?
Yes.
No? 2.303 equals log C minus gamma times 1.098 and minus 3.219 equals log C minus gamma times 1.386. So if I do the first equation minus the second equation, what will happen? The log C term will cancel out, and so it is minus 2.303 minus this 3.219.
Equal to.
Okay, so equals, so minus gamma, if I take it outside, it's 1.098 minus 1.386. Okay, so this as it is, the first equation minus the second equation. So minus 2.303 minus this term equals, these two cancel out, minus gamma times 1.098. So the minus gamma I'm taking outside as it is, times, so minus 1.386. So you just have to simplify this. So it is minus plus 3.219 minus 2.303 equals minus gamma times whatever is this. So this is going to be, so I think you can do from here, right? So 1.098 minus,
0.284.
right? So if you solve for gamma, it is going to be 3.18. Okay? Alright, so that's your gamma. So once you get your gamma, you can substitute for it in one of the two equations, and that will get you log C. Okay? So once you get log C, you can find what is C. Okay? So substitute for gamma in one of the two equations, say this one or that one. So first we'll find log C. So once you get log C, some value, how do you find C? E to the power of that value, because this is the base E. Log C means log the base E. So there's another log property. If you have log of, say, A to the base B is some K. What is A? B raised to K. Here the base is E.
Nothing in C.
Huh?
Yeah, we have nothing here, so that's why E, right?
This is natural logarithm. So you have to use the base E. So you know the difference in notation. If I say ln means natural logarithm, so that is equivalent to writing log to the base E.
That's accurate.
We don't write log to the base 10 as ln. We don't write like this. If you want to write the base 10 or any base, you write it like log, log to the base 10. So only in the case of natural logarithm, you can write ln. So if you do not know so far, it's time to know this, okay? Alright, so we get C to be 3.286. So of course you can substitute C and gamma in those equations and check if you get the answer, okay? Any question? Okay. So given the adjacency list of the vertices, so what I will give you is just this. Okay. So if you're given the adjacency list of the vertices, you want to determine whether the network could exhibit a scale-free property. Okay, so what is the scale-free property? Last time I said the kurtosis of scale-free networks is typically about 3. So if the kurtosis of a degree distribution is above 3, we say that network will exhibit scale-free property. Okay, so our target here is to find the kurtosis of the degree distribution. Okay, and this is the formula to find the kurtosis. So as you can see, to find kurtosis, you need to find the standard deviation of the degree distribution, as well as the average degree also. Okay, so let us see how to do that, just given the adjacency list. So with adjacency list information given like this, you can of course find the neighbors of each node, right? So first of all, find how many vertices are there. So it starts from 0, goes all the way up to 9. So there are 10 vertices, 0 through 9. So write down all the 10 vertices, and then just go through the list one by one. So 0 to 1, there's an edge between 0 and 1. Okay, so 0 has 1 as a neighbor, then 0, 2, 0, 3, 0, 4. So it follows the convention which we use to write adjacency list. So it has 0, 5, 0, 7, 0, 8. Then 1 has an edge with 3. So 1 has an edge with 0. So we don't repeat that information again. So it's understood. So which means you have to write also 1 has 0 as its neighbor. Okay. So 1 with 0. Then 1 with 3. So you can go on the right side. 1 with 0, then 1 with 3, 1, 5, 1, 6, 1, 9. Then 2 with 0, then nothing else. So 2 has just 0 as a neighbor. Then 3 with 0, then 3 with 1, then 3 with 4, 0, 1, 4. So look from both sides, because we need to know the degree of each node. Okay. So with this, we can easily count the number of neighbors for each node and get the degree of each node. So these are the nodes, and these are, so just count the number of neighbors, that will be the degree of that node. Okay, so this is your first step. So to get the degree of each node. Okay, so once you get the degree of each node, what can you do? You can find the P of k values. We have done this before, right? So how to do that? Find the degree values and count the number of nodes that have that specific degree. So the degree values that you see here are 1, 2, 3, 4, 5. There's no 6, 7. So 1, 2, 3, 4, 5, 7 are the degree values of the vertices. Now count how many vertices have each of those degree values. Okay? So how can you count? Just go through again the degree distribution. So there's degree 1 here. So just one vertex has degree 1. Then degree 2, there are 3 vertices with degree 2. Degree 3, 1, 2, 3. 3 vertices with degree 3. Degree 4, only 1 vertex with degree 4. Degree 5, only 1. Degree 7, only 1. So that is the count of the number of vertices with those degrees. So now we have to find the pk is nothing but the count divided by the number of nodes. So one node with degree 1, so 1 divided by 10 is the probability of finding a node with degree 1. Okay. Similarly, 3 divided by 10 is the probability of finding a node with degree 2, and so on. So the P of k values should of course add up to 1 because we're dividing by number of nodes. Okay. Okay. So now once you get the k, so degree is k, then P of k. The different ways, of course, we find the average degree. One way to find the average degree is k times pk, summation of all those, k times pk. Okay. You can also do what? Sum these up and divide by what?
So
The total number of vertices. So that's another way of finding average degree. Okay, all the ways we should give you the same answer. Then so k times pk. So just 1 times 0.1 plus 2 times 0.3 plus 3 times 0.3 plus 4 times 0.1 and so on. Add them up. So that is 3.2. So the average degree of the vertices in this network is 3.2. Okay. So first find the degree distribution like this, then the p of k values, and get the average degree. Any questions so far? Okay. So once we get the average degree, we can find the standard deviation and then the kurtosis. Okay. So we can build up a table like this. Of course, you can also do this in Excel. Okay. So if in exam, if it's a take home, if you do in Excel, print that Excel spreadsheet like this, and we can include it along with your answer. Okay, so the average degree is 3.2. So write down the degree values k, p of k. Okay. Then now that we know the average degree, we can find k minus the average degree square. So why we do all these things? So look into the formula. The formula for standard deviation is p of k times k minus average degree square. So we need to find this k minus average degree square for each value of k, and then multiply that with p of k, and then sum them up and take a square root. So that is why we are finding k minus the average degree 3.2 square. So it's like 1 minus 3.2, which is what, negative 2.2, square is 4.84. Then 2 minus 3.2, negative 1.2, square is 1.44. Then 3 minus 3.2, negative 0.2 is 0.04, square it. Then 4 minus 3.2, 0.8, square is 0.64, and so on. So find all those squares. And then, according to this formula, you have to multiply with p of k. So multiply p of k with k minus the average square.
So that square k minus k average square, that k average, the total average, right? Oh, okay.
Yeah, there's only one average.
Okay, I did see that.
Okay. So then 4.84 times 0.1 is 0.484. 1.44 times 0.3, 0.432. So once you get these, you can add them up. Okay. So if you add up all these values, you get 2.76. Then take a square root of that. It's 1.661. Okay. So that's the standard deviation. Okay. So the degree average is 3.2. Standard deviation is 1.66. Okay. So it's still not clear whether it could be like a scale-free network or not. So that is why we'll go ahead and also find the kurtosis. It's reasonably high, but not greater than the average degree. Okay, but it's little high. All right. So to find the kurtosis, this is a formula. So we have k minus average degree raised to 4. So that is why we go ahead and find k minus average degree raised to 4.
So kurtosis means you need to find the 4, right?
Yeah, the fourth exponent.
Yeah.
Okay. So that's called, like in statistics, average is called the first moment, standard deviation is called the second moment, kurtosis is the fourth moment. Okay, this is something for the third one also. So you can either square this up, 4.84 square could be this, or you can just say k is 1 minus 3.2 raised to 4. So it's up to you how you want to find it. Then 2 minus 3.2 raised to 4. Okay. So then multiply each of these values with p of k. Right? So then, according to this formula, just add them up. So if you add up all these values, you get 24.906, and divided by the fourth power of the standard deviation. So once you have standard deviation, you can plug that here, and the final answer is 3.27. So the cutoff point is 3. So if it's 3 or above, we can say the network will exhibit scale-free property, or it is heavy-tailed in nature. Of course, it's not far away from 3. So if you have two networks, the cutoffs of the degree distribution for one of them is 3.27, the other is say 10, then we can say which network is relatively more scale-free. So that is why we quantify all this stuff. Okay? So it's kind of on the borderline. Okay? Any question? Alright, so
sir, you said like over there 1.661 is less than average, but it's high.
it's less than average, but it's reasonably high.
It's looking high, but here the kurtosis comes like 3.27, which is also high, more higher than the average. So
yeah, kurtosis, there's no comparison with average. So for kurtosis, you have to compare with this cutoff value of 3. So there is some research work that has been done, and they found out if the kurtosis is above 3, the network can be considered to exhibit.
How you can say like the greater than 10 means how we know that value 3?
Yeah, so as I said, the 3 is as a result of some research work that was done in this area.
Okay.
So they did some mathematical analysis and they found out that the cutoff for kurtosis is
Oh,
3.
it's already fixed.
Yes.
If it's
Somebody has found from the research through some mathematical analysis that if the kurtosis is above 3, okay, then the network can be considered to exhibit scale-free properties.
that means the kurtosis value should be more greater than 3.
Right. So if it's less than 3, naturally the standard deviation also will be less, okay, compared to the average. So we can then say the network does not exhibit scale-free property. Okay. So that could be.
If it's the kurtosis is more than 3, then it's
It's going to be, we can say it exhibits heavy-tailed degree distribution. So what I mean.
okay, the less, yeah.
Yeah, it will go on forever. Okay. So if you do this example, we can get a feel of this. So before we do this, if you look at the degree values, node 0 is the only one that has degree 7, a very high degree. Then node 1, reasonably okay, high, fine. So the majority of them have degree 1, 2, and 3, right? So that is why, of course, 2 and 3 are more common. So if you plot it, of course, this is a small network. You cannot really expect to get a shape like this. But this is if you plot K versus P of K, you can see for 2 and 3 you have a high probability. And as the degree increases, the probability reduces. Okay? So let us now do this example and see how it is here. So similarly, I give you the adjacency list. The first task is to find how many vertices are there. So 10 vertices, 0 through 9. And just scan through the list and write down the neighbors as usual. So 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. So 1, 2, 3, 4, 5. Now for 1, 0, then 2, 4, 6, and 9. Okay? So you have to consider the other side also for larger IDs. So for 2, 2, 0, then 2, 1. So anything less than 2 will be on the left side, right? So then anything greater than 2 will be on the right side. 2, 3, 2, 8. So 0, 1, 3, 8. So for 3, less than 3 will be on the left side. So 3, 0. 3, 2, then 3, 6, 3, 8. So that is how you have to find the neighbors. Okay? So once you get the neighbors, you can find the degree of each vertex. So for node 0, you have 5 neighbors. Node 1, you have again 5 neighbors. Node 2, 4 neighbors, and so on. So if you just look at it visually, you can have a feel that the degrees are more or less equally distributed. Okay? And we'll try to quantify that. So the first step is to find the P of K values. So again, count the number of, first find the different degree values. So if you don't have a degree 1, you have 2, 3, 4, and 5. So these are the 4 degree values. Count how many vertices have degree 2. Okay, so 4 vertices, degree 3, 1 vertex, degree 4, 2 vertices, then degree 5, 3 vertices. Then just divide those count values by what? The total number of vertices, which is 10. So these are the probability values of finding a node with a certain degree. Okay. All right. So you can see the probability values. Node 2, degree 2 is 0.4, and 5, the larger value for degree is also high, 0.3. So it's not like very low. Okay. So the degree values are kind of relatively equally distributed. So let us go ahead and find the average degree, k times pk. So 2 times 0.4 plus 3 times 0.1 plus 4 times 0.2 plus 5 times 0.3. That adds up to 3.4. So that's the average degree. So once you get the average degree, you can build this table. So again, the k values, the degree values, pk, then k minus the average degree square. So average is 3.4. So 2 minus 3.4, negative 1.4 square, 1.96. 3 minus 3.4, negative 0.4 square is 0.16. And 4 minus 3.4, 0.6 square. So square them up, multiply with p of k. So multiply 0.4 with 1.96, you get 0.784. Okay? And 0.1 is 0.16, you get 0.016. So according to the formula, once you multiply p of k with k minus average square, sum that thing. So sum all these values, that comes to 1.64. So square root of that is 1.281. Okay? Now the kurtosis, we have to find the different fourth power of this difference, k minus average raised to 4. So 2 minus 3.4, negative 1.4 raised to 4. Okay? Then 3 minus 3.4, negative 0.4 raised to 4, and so on. Okay? And then multiply this with p of k. Then add them up. You get 3.5313 divided by the fourth power of standard deviation. So you get 1.31. So the kurtosis is well less than below 3. Okay? So that means what? We cannot say the degree distribution exhibits heavy tail pattern. Okay? So the degree distribution is not heavy tail. Okay? That's what we could conclude. Any question? Okay, so we should be able to do problem like this. Okay. So another way of asking problems around this is, I'll give you the k and p of k values. Okay. So once I give you the k and p of k values, you need to determine whether it exhibits a power law distribution or a Poisson distribution. Okay, so once I give you just the k and p of k, I won't give you this curve. So you have to first plot k versus p of k in Excel and see how the shape is. So if the shape is like this, it means it is a power law distribution, scale-free network distribution. If the shape comes out to be a bell-shaped curve, it means it is a Poisson distribution. So once you kind of come up with a hypothesis, so you're just plotting k versus p of k. Okay, sometimes it may not be a very smooth line like this, but you should be able to kind of make a guess, hypothesis, whether it is a scale-free power law distribution or a Poisson distribution for random network. So depending on what you decide based on the shape of this distribution, you go ahead and find parameters of the distribution. So what I mean by parameters of the degree distribution, we just did for the scale-free network, we found the kurtosis.
Sir, you said like if it's only like not like Poisson, what it is called?
See, we are seeing so far in two types of network, either Poisson distribution or scale-free power law distribution.
Yes,
right? So accordingly, I'll give you the data as that. It will be either a bell-shaped curve or it will be like this.
Or scale-free.
Or scale-free power law.
Got it.
So depending on how you see it, then you have to go further and determine the parameters of the degree distribution that you decided. So if it is scale-free, we just did. We have to find all the way up to kurtosis. Okay. If If it's not scale free, we can find the average.
Just now, what you said, scale, if it's scale free,
If
it's
it's scale
kurtosis.
free, go ahead and did like what we just did, find the kurtosis.
Okay.
Okay? If it looks like a Poisson distribution, we can go ahead and, okay, if it's scale free, okay, I'll take it back. You can find the kurtosis also. If it's scale free, since you're given K versus P of K, right? We can fit this and find the power law constants. What are the power law constants? P of K is C times K to the negative gamma, right? So we can fit the K versus P of K values and find the C and the exponent gamma. Is that clear? Okay, so let us see how to do that.
Yeah.
Okay, so since we have found,
If it's
if it's a Poisson, we'll see what to find. Okay?
if it's Poisson or if it's free scale also, you said like we can.
If it's Poisson, you cannot find this because it
Oh,
won't
okay.
because it has to be this pattern.
Oh,
The-
okay.
Right? A Poisson you won't be able to find such a distribution. So it has
It's
to
only
be like
kurtosis. It's only for scale.
power law.
For
Okay?
scale.
Scale free. So if the degree distribution, if K versus P of K comes out like this, then you can go ahead and try to fit this
Wow.
data to this model and find the constants C and gamma. Okay? You also find kurtosis and see what is the value, right? Okay, so let us see how to do this curve fitting now. So when we solved the first problem today, what did we do? We took logarithm on both sides and said log P of K is log C plus minus basically gamma times log K, right? So we have here K and P of K, so which means we know K, which means you can find log K and log P of K. So given K and P of K, you can find log K and log of P of K. So now take an Excel sheet and try to plot this. So you have to decide which is X and which is Y. So you see here, this is like log P of K equals some constant plus, or basically this is like what?
Y equals
Minus,
mx
right?
plus b.
What?
Y equals mx plus b.
Yes. So Y equals mx plus C or B.
Well, yeah.
Okay.
Right, c, yeah.
So log P of K, so you have a C here, so let us use B. So log C minus gamma times log K. So this is like Y equals M times X plus B. So your X is going to be log K, that's your X. Your Y is log P of K. So be careful, you choose which one is what, okay? So then using this as your X and this as your Y, try to plot them. And then, remember what did I say last
Sir,
time?
generally we plot like probability versus degree, right? So that's the thing here, right?
That is one way to plot K versus P of K. So that is the same thing here.
Yeah, same.
But we are taking logarithm so that we can try to, because this is a straight line. So
Yeah.
we have to now model this as a straight line.
Yeah, y equal mx.
Right, so you all know how to do this, right, in Excel. And then once you get the line, you have to do what? Right click and say, find add trend line. We did it last time, okay? So once you right click and say add trend line, so the original distribution will come out like this red curve, like this. It won't be a straight line. But once you right click on the red line, on any data point on that red line or curve, and click add trend line, you will see a straight line being fit. And on the bottom you can scroll down and also ask it to display the equation. Okay, we did that last time. So you scroll down and just click on that option, it will display the equation, so that is what you want. So in this case, it displays say y equals negative 2.7775x minus 0.1873. So that's what it displays. So from this, what can we say about the slope? So the slope is here m, which is negative gamma, right? So the slope we get from this equation is
2.775.
minus 2.7755, and that is negative gamma. So the minus minus can cancel out, so your gamma is 2.7755. Okay, so gamma is always going to be positive. So don't make a mistake of coming up with a negative gamma.
So how you figure out?
Okay, so from this equation, m is negative gamma.
Oh, okay, yeah, okay.
And m, according to the equation from Excel, is m is negative 2.7755, and m is also negative gamma.
Got it.
So put that equal negative gamma, the minus minus can cancel out, so gamma is positive 2.7755. Okay? Clear? No? Should we do it in Excel?
Yeah.
You can do it?
Yes.
Everybody else?
Mm-hmm.
Okay. Alright, so once you get gamma, how can we also find the constant C? Constant, this is the B, right? That is negative 0.1873. So that is log C, right? So B is log C here. So once you again know log C is negative 0.287, sorry, minus 1.1873. So how can you find C then?
Log both sides?
It's already have a log.
Oh, raise it, oh, E raised
to the power.
yeah.
E to the power of minus 0.187. So you should know how to find e to the power of something in your calculator, okay? So that will come out to be 0.829. Okay? So we can now write the power law. P of k is the constant C, 0.829 times k to the power of negative 2.7755. Okay? Now the gamma value, as I said last time, for scale-free network is typically between 2 and 3. Okay, so it is fitting within that range. Okay? Any question? Okay, so I have another example that will be like a Poisson distribution. So you have k versus p of k values. So if it comes out like this, a bell-shaped curve, then it's not power law. It is Poisson distribution. So let us see what parameters we can find for a Poisson distribution. Because we can find average degree and the standard deviation. So for this we can find the kurtosis. And the kurtosis has to come less than 3, right? Because it cannot be greater than 3 for a Poisson distribution. So you all know how to do this, right? So given k, p of k, find first the average degree, k times p of k, summation, that's the average degree. Then k minus average square times p of k, sum it up, that's standard deviation, then the kurtosis. Okay? So it comes out to be 2.852. So it is close to 3 but still less than 3. Okay, so we cannot say it is scale-free in nature. Okay, so any question? So this sort of thing is on written exam. Okay, so let us move on. Now, so the power law distribution that we saw so far, we assume that it starts from the smallest possible value of degree. So for k equals 1, okay, so we see the pattern. But for real world networks, so this is more for theory, okay, theoretically you can say the power law distribution that will start from k equals 1. But if you plot the degree distribution for real world networks, the K is P of K, you could see there is a range of degree values for which you don't see this pattern. So you start seeing this pattern only after certain cutoff. Okay, so that is called the X minimum, or the degree minimum. Okay.
What is cutoff here?
Like you don't see the, like if you see the shape of this curve, right?
Okay.
For some citation network. So the K versus P of K, you don't see this kind of sharp decrease and then a constant slowly decreasing trend right from the beginning. You see this pattern only after some minimum value. Okay, so you don't see the power law nature in this range or this region. Okay, so we can say there is a minimum value starting from which the real world networks will exhibit the power law pattern of degree distribution. Okay, so such a pattern has been observed for several real world networks. So this is some data. So some people have some research on these different real world networks, and they found the minimum value starting from which the power law distribution is seen, as well as the value of this exponent gamma. Okay, so once you can, like we just did, we can fit the K versus P of K and try to find the exponent gamma. Okay. Okay, so this is something we already saw, the relationship between K max and K min, okay, and why gamma cannot be, say, less than 2. Okay, so gamma has to be greater than 2 to make some sense for a scale-free network. If gamma is less than 2, you will come out with K max greater than the number of nodes. That's not possible. Okay. Okay. Now, something about the average path length. For a random network, we saw a formula, right? What was the formula for average path length? Log n over log average degree. Isn't it? Something like that. So like that, we can also have formula for average path length, okay, for scale-free networks. So since the gamma is a parameter, right? So for different range of values of gamma, we have different formulas for the average path length.
So
Yes.
average path length, as you said, is average path length is the same like average cluster coefficient, right?
Now, there are two different things. Path length means what? The number of edges on the shortest path between any two
Yeah.
vertices. So is that the same as clustering coefficient? No, right? Okay.
No, last class you said something like you will trick on the question or something.
What did I say?
You said something, you showed a question over there and the last one.
Oh, that was probability.
Oh,
So that is for random network again. So for random network, what is the clustering coefficient of any node? For a random network, what's the clustering coefficient of any vertex or node? Same as P-link. It doesn't matter how many neighbors a node has. The
Yeah.
clustering coefficient is same as the probability for link between any two nodes. Okay. And this was the formula for the average path length there, log n divided by log of average degree. And this is for random network. Okay. So let us now see the formula for average path length for scale-free network.
okay. Yeah, that's different.
Okay. So now, as I said, the gamma values can start from 2. So if gamma is 2, okay, then it looks like a hub and spoke configuration. So what is hub and spoke configuration? Like a star network, which means you have the hub node in the center and all the other vertices are attached to the hub. Okay, so this is how a scale-free network will look like if gamma is 2. Okay, okay. Now, for such networks, if it's like this, so this is also called a star network because it looks like a star. Okay? What is the average path length between any two nodes? Majority of the pairs are like one node here, another node here. So between these two nodes, the path length is two edges. Okay? So of course you have paths from the hub to every node, but the majority is like the number of pairs. Okay, is dominated by the vertices that are not hub. Right? So the average path length is a constant because it's just like basically 2. Okay, so we can say if gamma is 2, the average path length is a constant. It depends on the number of pairs and so on. Okay. Now, so the interesting thing will come out if gamma is greater than 2. So if gamma is within this range, between 2 and 3, okay, then the formula for the average path length is this. If you read one of the references I have given, the syllabus or it's also available online. It's a free book. Okay, so the author is Barabasi. So if you go through his book, he has shown the derivation.
Most of the your link, most of the links are Barabas, belongs to Barabas. You put it.
Yes, because that's like a good reference. Okay. So if you go through Barabasi's book, he has showed the derivation. And even for some of the other cases where I said just consider this as a formula and we not go through the derivation, if you go through Barabasi's book, you can go see all the math behind those formulas. Okay. So behind this there's a long derivation. So we are just taking the final formula. So the average path length is log n divided by log of gamma minus 1. Now, so this is for gamma between 2 and 3. If gamma is 3, then this is log n divided by log n. Okay. Now, if you, I think I introduced this terminology before. So let us finish this. So if gamma is greater than 3, the average path length is log n. Right? So now, these two cases you have log n in the numerator. This is just log n. This case you have log n. So if the average path length is proportional to log n, then we say the network exhibits the small world property. Remember that I said? So even for random network, the average path length was what? Log n divided by log average degree. So you have log n in the numerator. So if the average path length is proportional to log n or is some function of log n like this, we can say the network exhibits small world property. So you see average path length for a random network is what? Log n divided by log k. So you have is something proportional to log n, right? Log n is in the numerator. So similarly, you also have for a scale-free network, if gamma is 3, it is log n divided by log n. If gamma is greater than 3, it is just log n. So all these things are like what? Similar expressions where log n is in the numerator. Okay? So we can say if the average path length is proportional to log n, the network exhibits small world property. Again, small world means the reachability between any two vertices. It's not proportional to n. You may have n like it's a million vertices, but the average path length is log of n.
Small world property.
Small world. The name itself indicates what? Small world. What does small world means?
Means like it's the closeness is high.
The reachability between any two vertices is
Okay.
high. Okay. So even in Facebook, there is some analysis. The average path length of a Facebook network is typically around 4 to 6, something around that. So which means you may wonder, a lot of people in Facebook, right? But how do I know somebody? How is just the path length is 4 to 6? You know someone, and that person knows someone, and so on. So On average, of course, it's not between any two vertices. Between some two vertices, you may have a path length of 10, but on average, it is something like 4 to 6.
So when Facebook created the person, means they used this concept.
No.
It was not created. So
This is not. So this is like the behavior of social networks.
yeah,
Okay,
but
so
means the concept used is there. It's previously invented.
no. This is just like what we observe in reality.
Okay.
Okay. Of course, theoretically it was derived like this. So theoretically this expression can be derived. Okay, and this has been also observed in reality in social networks and several other networks. Now, if the average path length is proportional to log of log n, that means even smaller, because already log n is smaller, right, compared to n. If you take logarithm of log n, see what I mean? So if n is say 1 million, if you have a calculator, you can find out what is log n to the base e.
Log n of 10 to the power 6.
Taking so much time to find log n. 13.8, okay. So use the base e, right?
13.81.
Okay. So now find log of log n. So find log of 13.81. Be some what? 3 or 4. What is that?
Log of 13.81.
Mm-hmm.
2.62.
Okay. So that is the kind of relative magnitude. So you can see, even though like Facebook and large social networks can have millions of users, the average path length between any two nodes, which we have 1 billion nodes, is going to be proportional again to log n. So 13.81. Now if you take logarithm of this, it's 2.62. So it's even smaller. So that is why if the average path length is proportional to log n, such networks are considered to exhibit the ultra small world property. So ultra means even smaller. Okay? So ultra small world. And if it's proportional to log n, it's called just small world. Okay? Is that clear? Any question? Alright, so again, we are seeing this. So scale-free networks is typically between 2 and 3, where the standard deviation is mostly greater than the node degree. The standard deviation of node degree is greater than the average. So now to have a feel of where the random network falls under, the standard deviation for random network is square root of k, right? So for the average degree that you get with the, we did all the analysis, right? For different values of gamma, we found the p of k, and then based on that, the average degree. So for these values of average degree, the square root of average degree comes out like this. Is that clear? Just take square root of these numbers. But this is for what? Random network. So if you find the standard deviation of node degree based on scale-free network, it comes out like this. So you see how high, how far away they are, the standard deviation for random network and the standard deviation for a scale-free network. So of course the standard deviation for scale-free network starts decreasing as you increase gamma, and if once gamma becomes greater than 3, right, you can see it kind of approaches the standard deviation of the random networks. So that is why we say if gamma is between 2 and 3 scale-free regime, and if gamma is above 3, we can say it is the random network regime, or the region, okay? if gamma is less than 2, it's anomalous. Why it's anomalous? Because the network is not well defined. As we saw, if gamma is less than 2, the maximum degree can become more than the number of nodes. So that's why it says it's anomalous regime. Is that clear? So we can.
And why it's anomalous?
We saw last time the analysis, the formula, where if gamma is less than 2, the maximum degree can become greater than n. Remember that? Substitute for given n, and let us say k minimum is 1. So k max is going to be, like, if n is 100, what is going to be k max for gamma 1.5? 100 raised to 1 divided by 1.5 minus 1. What is that? This is 2.
Yeah, 2.
So 100 square. So you have only 100 nodes. So the maximum degree can be only 100 minus 1, 99. But it comes out to be 10,000. So which means the problem is because of the value of gamma. So gamma less than 2 is not realistic.
Okay. A gamma should be more than 2.
Right.
2 or more than
2 or more. It cannot be even 2. 2 means you get k max 100. So it has to be even slightly above 2.
Oh, okay.
But
Slightly
it's
above 2.
just for this example because your n is 100.
Okay.
It may
it's
change.
only for this example.
No, if you change your n.
If you change your n, that still holds true?
Yeah.
Oh, okay.
Yeah.
All
Yeah,
right.
it's for whole.
Right.
Okay.
Right. So that's why this plot here is in general. Gamma has to be greater than 2.
Okay.
Okay, so between 2 and 3 is the normal range for scale-free networks. And several real-world networks. So based on similar analysis we just did, by doing the k, this is P of k. So this is just taken from Barabasi, a screenshot. So that's why it's red in color. I could not change the color. Okay, so if I take the k and P of k and try to fit the curve and so on and find the constant c and gamma, like we just did for small network. So people have done that for the real world networks like World Wide Web, several networks, protein networks and so on. So if the network is scale-free in nature, they found the gamma to be between 2 and 3. And if it's more like a random network, they found the gamma to be above 3. Okay? So none of the real world networks had gamma less than 2. Okay? So that also kind of correlates with the analysis we just did with that example. Okay? Alright, so the average path length is also shown here. So between 2 and 3, average path length is log n. If it is above 3, we can say it's log n divided by log k because log average degree because it is random network. Okay? So let us do a problem based on all of these now. Okay, so this may be even more, it's better to look at. So these are again real world networks. Okay, citation network, metabolic network, internet, collaboration network, and so on. So you try to plot the average degree that you observe in each of these networks versus the standard deviation of degree. As I said, for scale-free networks, the standard deviation is typically much larger than average degree. Okay, so for this average degree, again, the dotted line indicates the square root of average corresponding to random network. So only one network, like a power grid network, has standard deviation that is well within this dotted line. All the other real world networks have standard deviation above this dotted line, which means they have a standard deviation is well above what is seen for a random network. You can see if the average degree is 8, for example, the world, what is it for 8? The collaboration network standard deviation is 10. Let us take the World Wide Web. The average degree is close to 4, whereas the standard deviation
So
is
it's
close
true?
to. Huh?
It is like true data?
Yeah, this is real world network data.
Okay.
So the average degree for the World Wide Web based on incoming edges. Okay, so when I say in, it means incoming edges.
How we know the Means it's already written somewhere?
You run some scroller, yeah, it's already on some people. It's all big data.
Okay,
So some
yeah.
people have found that information. So metabolic networks of some organism, again based on the incoming agent. So you have in and out if it's a directed graph, right? So if you have in and out, it's directed graph. If you don't have in and out, it is what? There's no, it's undirected. Okay, so the internet is undirected, collaboration, okay, and so on. So for all the cases, okay, so you find the standard deviation to be above average. Okay, so which also indicates most of the real world networks are scale free in nature. Okay. Any questions so far? Okay, so let us do a small problem and then you can leave. Okay, so consider what? Consider a scale-free network of 100 nodes, and a network is modeled using power law. P of k is c times k to the negative gamma. The minimum and maximum degrees are given as 3 and 60. We need to find the power law exponent, gamma, the constant c, and the average path length. So something that's similar to what you have seen so far. So what are all given? K min, K max, and then the number of nodes, right? So K max is 60, K min is 3, the number of nodes is 100. So we need to find C, gamma, and the average path length. Okay? So since K max and K min are given, we have to use this formula one way or the other. Okay, so n is also given. So I think this is a good fit. So K max is known, K min is known, n is known. So we can now find gamma. Right? So even though gamma is an exponent, we should know how to solve this. So let us do that. 60 is K max, 3 is K min, 100 is n, 1 raised to 1 more gamma minus 1. Right? So this is what it is. So how do you solve for gamma? Using the logarithm. Okay, so 60 over 3 is 20 is 100 raised to 1 more gamma minus 1. So if I take logarithm on both sides, log 20 is 1 over gamma minus 1 log 100. Is that clear? If I take logarithm, the exponent comes before. So now we can say gamma minus 1 is simply log 100 divided by log 20. And that comes out to be 1.54. So since gamma minus 1 is 1.54, so gamma is 1 plus that, so it's 2.54. Okay? So
log 100 to
log 100 all to the base e, natural logarithm. Okay? So once we find gamma, we can do what? Find what else? To find the constant c. Remember at the beginning of this topic, we saw this summation, right? So what did I say? For a given gamma, we can find the constant c, like what? C equals 1 divided by all values of k, starting from 1 to infinity. Now you may wonder how to do this. Again, open an Excel spreadsheet like we did before. Type all values of, now, should I type all values of k? No, just use this, because the given k min is 3 and k max is 60. So that's a thing you have to be careful. So k min, k equals 3 to 60. So in the Excel spreadsheet, type k 3 up to 60. You don't have to type 3, 4, 5, 6. You know how to do that in Excel automatically? Not yet? So let us say start with 3, right? Showing up. Okay, so I want to type 3, 4, 5, 6 up to 60. So equals B1 plus
One.
1. So that is 4. So then what you do
Answer
is,
should be the lambda should be gamma should be 1.65.
you got 1.65,
Yeah.
maybe some round up error. No, it's not one, it cannot be that different. It should, gamma minus 1 is 1.65. Then gamma is 1 plus that. Okay? Alright, so then copy this cell because it has a formula, the previous cell plus 1, right? So that's the formula we want. So just scroll it down, scroll up to say some number. You don't have to, then you can delete those cells, then paste. So you got all the values. So
Which
you-
values?
from K, I'm just showing how in Excel you can automate this. You don't have to manually type 3, 4, 5 up to 60. Okay? So then what you do?
You just scroll it. You just
Yeah, but you have to, there's a formula here. This is B1 plus 1, B2 plus 1. Okay? Alright, so now the gamma is what? Gamma is
2.54.
good, 2.54. So how to enter that? So B1 rise to minus 2.54. So this is exponent. Okay? So that is the K rise to negative gamma.
Mm-hmm.
So now copy this and go up to 60. Okay? And then what is that formula there? The summation of all the K rise to negative gamma. You see it has started to reduce reasonably well.
So what you did in the first shell, in the what's the formula? What way? 3 by 2.54?
You're talking about something else.
No,
What is-
over there, what formula? In
Yeah, so gamma is 2.54, right?
Yeah.
So then this is the formula. The C equals 1 over, remember that we saw in the beginning of this module topic on scale free networks?
Yeah. 1 by 2.54?
1 by
No.
1 divided by the summation.
Oh, okay.
So what is inside summation? K rise to negative gamma. And the K ranges from K min to K max.
Mm-hmm.
So that's what we are doing here. So K min is 3, K max is 60. Okay? And the second column is what? K rise to negative gamma. So each of these K values rise to negative 2.54. So all you have to now do is find the summation. So what is the summation? Equals, so actually the formula is 1 divided by summation. So you can do it right away. So 1 divided by the summation, C1 to C60 will give you the summation.
Don't you just need to go to C 58?
Yeah, you're right. Because it's 3 to 60.
Yeah.
Okay. Alright, so that will get you the 6.252175.
So how you get the C section?
Which one?
The C section means over there. I
So
know.
this is the formula.
Okay.
Not even like a formula based on fundamental. P of K is what? P of K is C times K to negative gamma. So if I sum over all
Yeah.
K, this is equal to 1. So based on that you can get this. Okay? So
C
once,
to K, okay.
once you find C and gamma, you can find average path length. How to find average path length? You have to decide based on the value of gamma we got. So the value of gamma we got is 2.54.
Yeah.
So that is why I showed you the range of formula for different values of gamma. So you have to use, gamma is in this range. So you have to use this formula, log n divided by log of gamma minus 1. So n is what, 100, gamma is 2.54, so plug in here and that will give you the path length.
No, in that section, how you got the value? That's in Excel sheet in the second.
K rise to negative gamma. So K is 3, 4, 5 and so on, right?
Yeah.
So type equals the K, that cell is B1, so we have the C column. So it's C column first cell. So B1 rise to negative 2.54. Because the B column is your K values. If K is 3, You want to find 3 raised to negative 2.54, you do like what? Equals B1, because this is B1, cell 1.
Oh, means 3 to the power 2.5.
3 to the power negative 2.54. Then copy this formula with this equal to sign and paste it. So that will find B2 raised negative 2.54.
Or you did like k to power negative gamma.
K to the power negative gamma.
Okay.
Okay? Alright, so with that we can stop today.